For topic 8, we're going to add and subtract vectors algebraically, and this is really not going to be that difficult at all. It's fairly straightforward, just basic arithmetic, okay? Please do recall that we're going to be looking at magnitude again too. So if you have vector v equals a sub 1 times vector I plus b sub 1 times vector j, that's going to be the position vector a sub 1, b sub 1, okay? And the magnitude of that, we just take the square root of the A component squared, which is the horizontal movement, and then we take the B component, which is the vertical movement, we square that, okay? Now, not too bad at all right? So we've already found magnitude of vectors in the previous video. We're going to do a little bit more of that one in this, but it's nothing too scary. Okay. Now steps to add and subtract. Okay. So we're going to have two vectors. We're going to call them V and W. And please do remember, there are two ways that we can represent vectors. We can represent vectors with like the little bar over top, or we can do like a kind of like a heavy bold print, okay? You'll see the bold print like a lot of times in typed documents, like in books or online, but by hand we use the little hat just because it's a lot easier to do. So I've used a mix of them. So like you can see the little hat, and then I go bold and then bold. So like there's going to be a mix of them. Just know they mean the same thing. So if you see that like super heavy bold, it means it's a vector. If you see the little bars on top, it means it's a vector. There's no difference between those. Okay. So we're going to have vector v equals a sub 1 I plus b sub 1 times j. So remember, I and j are vectors. So that's going to be the position vector that we have right here, a sub 1, b sub 1, okay? And then we're going to say w is a sub 2 times vector I plus b sub 2 times vector j. It's going to be the position vector, just a sub 2, b sub 2, okay? So these are two vectors. We have the position vectors. They're a sub 1, b sub 1, a sub 2, b sub 2, okay? Now, how in the world do we add these? Well, all we have to do is add the horizontal components and then add the vertical components. It's literally it. We add the A's and then we add the B's. To subtract two vectors, we subtract the A components, we subtract the B components. Order does matter, so make sure you get the right order, okay? And that's it. And then if we have a situation like down here, this isn't adding or subtracting. This is where you take a vector and multiply it basically by a scalar. All you have to do is take the scalar and multiply it by the A component, and then take the scalar and multiply it by the B component. So you can almost like distribute that scalar inside, okay? So all pretty easy stuff, nothing terribly scary at all. And we get to practice. I think I have 3 full examples because sometimes the easy stuff, we don't practice it enough because it is easy, and then that's where we make goose. So we've got like 3 full examples here. Okay, so for example 9, it says that V is going to have, it's going to be the position vector 6 comma negative 2. So you can see we have it in component form, 6 times vector I minus 2 times vector J. And then we have vector W, which is 2 times vector I plus 5 times vector J. So I like to use the position vectors. They're just less clunky. They're less busy. I like them. They're just more palatable for me, okay? So if we want to find vector v plus vector w, we want to add these two vectors, all we have to do is add the a components, okay? So essentially we want to take a sub 1 plus a sub 2, b sub 1 plus b sub 2, where this is a sub 1, b sub 1, a sub 2, b sub 2, okay? So a sub 1 is 6, b sub 2, or a sub 2 is 2, b sub 1 is negative 2, b sub 2 is 5. So when we add our a components, we get 8. When we add our b components, we get 3. So we get the position vector 8 comma 3. Or if we wanted to, we could write this in component form. We would just get 8i plus 3j, and that would be the sum of these two vectors. Hold on, my sock just decided to like completely fall off. Let me write this one a little bit better. I want to put what they're equal to out front. So this would be V plus W equals, and then V plus W equals. Okay. Now, if we were going to subtract them, it would be the same thing. We would just subtract the A components, subtract the B components. So if we have V minus W, that would equal 6 minus 2, and then negative 2 minus 5. So that would equal 4, comma, negative 7. So we could say V minus W is 4I minus 7J. And that's it. And I'm not really torn up about which format you use. I do want you to understand both and how to can kind of like write either one in the other format, but either one's fine. I prefer the little pointy brackets, the position vector. All right, next we have V and W. So we're going to do a couple of things here. So we have that V equals 6I minus 2J. W equals 2I plus 5J, okay? We're going to find 5 times V. We're going to find 2V minus 2W, and then we're going to find the magnitude of V. So we're going to do 3 different things here. None of them are terribly difficult. So if we're going to take a vector and multiply it by some scalar, this is basically going to be the same thing as 5 times A, 5 times B if we wanted to write it as a position vector like in this format, okay? So all I have to do is I have to take my A component and multiply it by 5, so I get 5 times 6, and then I get 5 times the B component. So when I multiply this vector by 5, I get 30 negative 10. And think about what that means, okay? We know that we're dealing with a vector that has some kind of magnitude, okay? If we take a vector and we multiply it by 5, it's essentially just elongating that vector. So you could plot the original vector, you could draw the original vector and then take the vertical and horizontal movements and multiply them each by 5, and you would get this 5 times vector v. It's just going to be that same vector, same direction, just elongated, okay? So we would get that 5 times vector v is this. Okay, now you can take 2 times a vector and subtract 2 times another vector if you wanted to, and we're going to do that very thing. Okay, now you can do this 2 ways. You can find 2 times v, 2 times w, and then subtract them if you want to. You can do it all in one step. It really just depends on what you're comfortable with and what your level of organization is. So for me, I'm going to write them, I'm going to kind of multiply them both by the 2 first, and then I'll do my subtraction second. So I'm going to figure out just what 2v is. Well, it's going to be 2 times the horizontal component and then 2 times the vertical component. So it is going to be 12 negative 4. So that's 2v. Okay. Now I'm going to figure out 2w. So that is going to be 2 times the horizontal component, which is 2. And then it's going to be 2 times the vertical component, which is 5. So we get 4, comma, 10. And then finally, we're going to do our subtraction. So I'm going to take this right here and subtract this right here. So I'm going to get 12 minus 4, and then negative 4 minus 10. Don't put a comma, put a minus. And so we can finally say that 2v minus 2w is 8, comma, negative 14. So it has a horizontal movement of 8 and a vertical movement of negative 14. Now, I could also write this as a vector in component form. So I could say 2v minus 2w is 8I minus 14j. Either one is fine. And if I did the same thing up here, I could also do 5v equals 30I minus 10j. You could write that one that way too. And then finally, let's find the magnitude of v. Remember the magnitude, you just take the square root of the a component and add it to the b component, square each of those. So the square root of the a component squared plus the b component squared. So we are going to get, well, for vector v, a is 6. We're going to get 6 squared. B is negative 2, so negative 2 squared. So we get 36 plus 4. So we get then the square root of 40. And we do want to see if we can simplify this, okay? So when we simplify radicals, we just want to see, is there a perfect square that we can kind of simplify out of this? And in this case, there is. I could rewrite the square root of 40 as the square root of 4 times 10, which is the square root of 4 times the square root of 10. The square root of 4 is a perfect square, so I would just write this as 10, or 2 square root 10. Ta-da! Okay. Now one more. Let's see. I have like a fan that has like a battery in it, and the battery's about to die, and I'm so sad about that. It's so soothing and comfy with it. I just need to charge it, but it's about to die right now. So, okay. So for example 11, it's kind of the same thing. We're going to take one of the vectors and multiply it by a scalar. We're going to take both vectors, multiply it by a scalar, and then subtract it, and then we're going to find a magnitude. So we're just kind of practicing this again. None of this is particularly difficult. You just need to be careful, watch like signs and little things like that. Okay, so we have that. Ooh, have we talked about this yet? I was about to say, I don't know that we've officially talked about this, but we're going to talk about it. You can have a vector in three components, okay? So as I'm going to try my hardest to draw this, this is kind of hard to draw, but we live in like a two-dimensional world so far. So we have a y-axis, we have an x-axis, okay? So we can go left, right, we can go up, down, okay? When you have three components to a vector, you're doing something a little different, okay? So you're dealing with something kind of like this. Okay, so think of this as an x-axis, this is a y-axis, and this as a z-axis. Okay, now we already know from earlier that I and j are basically unit vectors, and they just tell us a direction that we're traveling. So we had that I was a unit vector in the x direction. We had that j was a unit vector in the y direction. And now what we're doing is we're like, hey, guess what? We also have a k, and a k is in a z direction. So is it going to let me draw green? There we go. So this would be the vector, the unit vector k. Okay, so if you have a vector that has three components, there's three possible directions. Okay, so it's telling you three different ways you can move. It's just a three-dimensional space. I don't want you to get too bent out of shape about this. This is something you're going to talk about way later in math, okay? But for now, just understand this is kind of what's happening. So we can go left, right, up, down, backwards, forwards, kind of, okay? So there you have it. So that's where this K thing just sort of appears from, okay? So the good news is when you're adding or subtracting vectors in three components, it's the same thing. You're going to add all of the A's, all of the B's, and then all of the, we'll call them C's or whatever. And then you can do the exact same thing when you're finding like the magnitude, okay? So you're just going to take the square root of the A component, the B component, and then whatever we want to call that third component, let's call it a C, okay? So don't get too lost. It's like the exact same process, just like an extra layer to it. Okay, so let's get rid of that. Okay, so for example 11, we have if vector v equals 2i plus 3j minus 2k, and w equals 3i minus 4j plus 5k, then find the following. Well, let's just acknowledge that if we wrote v as a position vector, it would look like this. It would be 2, comma, 3, comma, negative 2. We just have that third component. And then we could write w as 3, negative 4, 5. And again, I like these position vectors a little bit better. Okay, so if we wanted to find 3v, we're going to take those three components and we're going to multiply them by 3. So 3v would equal 3 times 2, 3 times 3, 3 times negative 2. So we could say, well, 3v, y'all, is 6, comma, 9, comma, negative 6, okay? And then if I wanted to write it in component form, I would just say, well, 3v equals 6i plus 9j minus 6k. Oh, my fan finally died. I'm so sad. Okay, now for part B, we've got to do 2 times V minus 2 times W. So I think I'm going to do like I did in the previous example where I'm going to figure out what 2 times V is. I'm going to figure out what 2 times W is. Then I'll do my subtraction. For me, that is easier to keep track of. Just depends on the person. You might be able to do this all at once, and that's awesome. Do that, okay? So for me, I'm going to figure out 2v. So that is going to be 2 times 2, 2 times 3, 2 times -2. So that is 4, 6, -4. And then 2 times vector W is going to be 2 times 3, 2 times -4, 2 times 5, which is going to be 6, -8, 10. And then I can really, really easily subtract them. So for me, this is easier. You do what makes you the absolute happiest. So we are going to get 4 minus 6, 6 minus -8. Please, please, please watch your signs. -4 minus 10. So we would finally say 2v minus 2w equals, let's see, that's going to be -2. 6 minus -8 is 14. -4 minus 10 is -14. And if we wanted to write this in component form, we would say that 2v minus 2w is -2i plus 14j minus 14k. So either of these are fine. Okay, and then finally we want to find the magnitude of vector v. So even though it has 3 components, it does not really change the formula. We just have like an extra layer to it. There's nothing like special and crazy. So this is going to be the square root of the a component squared plus the b component squared plus, let's just call it the c component squared. So we would say the magnitude of v is going to equal 2 squared plus 3 squared plus -2 squared. So we would get, let's see here, 2 squared is 4, 3 squared is 9, -2 squared is also 4. So let's see, 4 plus 9 plus 4 is what, 17? And that's as good as it's going to get, y'all. That's not going to simplify any better. So that would be our magnitude, okay? So don't let the 3 components flip you out. It's just this like sort of a 3D representation of what can happen. It's nothing that we're going to get too bent out of shape about at this point, okay? So in the next video, we're going to talk again about the unit vector. It's going to come back. We're going to talk about direction and magnitude, and then I think that's it. So it's 86 hours later, but I think we're getting close. I need to find another fan. This is really just tripping me out. The mine died. Anyway, best of luck to you all while I find my fan.